Alrighty, welcome back to 11.5. We're talking about the short run behavior of rational functions now, and where long run or end behavior of rational functions, where that was looking at when x is approaching infinity or positive infinity, right? Infinity or negative infinity. Short run behavior is looking at when x could be just some like specific number. So what I want to do is I kind of want to summarize this idea right away and just talk about, so if in a rational function, because that's what we're talking about here, so in a rational function, if x equals some number, right? So let's say if x equals a, okay? Just understanding that this is just some number. If x equals a causes, and then we're going to look at this in three different cases for a rational function. Remember, a rational function is a fraction of two polynomials. So if, when x equals a, it causes the numerator, and only the numerator, to be equal to 0, then the rational function, right, the whole piece, the whole function, about the number 3, right? So like, let's say when x equals 3, you plug that into the numerator, and it causes the numerator to be 0, and only the numerator, nothing else becomes 0, but just the numerator, then there's an x-intercept. Okay? All right, next case, what do you think it might be? Well, how about only the denominator? So if it causes only the denominator to be equal to 0, then the rational function, well, what do you guys know about when the denominator is equal to 0? What's going to happen? Can we divide by 0? No, we can't. And what happens is really close to 0, if you're dividing by a really small number, well, dividing by a really small number is actually going to output a really large number. So you're going to kind of like, the function's kind of fly off to infinity. And then on the other side of 0, which is negative, but it's negative, very small magnitude number, right? And we're dividing by it. That's going to shoot down to negative infinity. And so what we're going to create is a vertical asymptote. So the rational function has a vertical asymptote at x equals a. Right? So again, if we're talking about some other number, let's say we're talking about when x is -4. When x is -4, the denominator, and only the denominator, is equal to 0 when you plug -4 in, then that rational function has a vertical asymptote at x equals -4. Okay? And the third case, which I just realized I was just writing and you couldn't see. My bad. So there's the second case again. Only the denominator, if when x equals a, only the denominator is equal to 0, then the rational function has a vertical asymptote at x equals a. The third case, what do we think the third case is going to be? Well, how about both the numerator and denominator. So both the numerator and denominator are equal to 0. Then the rational function and this is where you would have something like 0 divided by 0, which doesn't really make sense. And if you ask Siri what 0 divided by 0 is, you get some like funny response or something. It's kind of interesting. So the rational function has a hole. So there's a hole in the function at x equals a, at whatever value we're talking about here. So if we're talking about plugging in a value of x equals 1, and when you plug that 1 into the rational function, into the whole function, if the numerator becomes 0 and the denominator becomes 0, so both of them are 0, then it's a hole, okay? So looking back here, these three cases will pretty much tell us about the short-run behavior of a rational function, okay? So let's take a look at the book. I'll just leave that up there for now. So in the book, we talk about zeros and vertical asymptotes. So we have an example here, x plus 3 over x plus 2. And if we want to solve this for the zeros, well, if we look back at our notes, if only the numerator is equal to 0, that's a solution, that's an x-intercept, right? So that's how we do it. So we set the numerator equal to 0, and now we can find, okay, well, what are my x-intercepts? So in this case, x plus 3, you solve that, well, we know that that means x is negative 3. And that negative 3 would not cause the denominator to be 0, right? So that's good. That's a x-intercept. Okay? To find the vertical asymptote, we would take this x plus 2. We would take the denominator, set it equal to 0. We'd solve that. Obviously, that's x equals negative 2. And so we know there is a vertical asymptote at negative 2. Okay? There is no value, there's no single x value that I can plug in that would lead this rational function to be 0 over 0, right? And so there's no hole in this function at all. Okay. Let's take a look at rational functions overall. Book kind of has a nice little summary here. We have the fraction of two polynomials is the rational function, and the long run behavior and the horizontal asymptotes are given by the leading term over leading term. Okay, that's what we talked about last time. The zeros of the function, or the x-intercepts, are the same as the numerator's zeros. The vertical asymptotes are the same as the zeros for the denominator, okay? And then we get down here and it talks about finding a formula for a rational function from its graph. So let's take a look at that. So for example, let's take a look at example 3. We're going to have to put kind of all of our, there we go. We're going to have to put all of the things about rational functions that we know together to kind of create a rational function based on this graph. So based on the graph, what are some features we see? Well, first of all, we should kind of go over this, like the standard form of a rational function, which before, like a rational function, which I just sometimes use as r of x, and then I do what the book does with p of x over q of x, right? These are both polynomials, but then it's also important to remember that this can be scaled just like any other function. So there can be a coefficient out front, an a value that we would have to solve for, just like we've done with many other functions. So let me try and make that an a. Okay, so there's our rational function form. Based on this graph, what features do we see? Well, the first feature that I like to notice is the x-intercepts. So there's an x-intercept at -1. So what does that tell me about the numerator? Well, if it's an x-intercept at -1, thinking back to polynomial functions, that means that that polynomial function is x plus 1. Okay? And it just crosses, right? It doesn't touch and turn. It doesn't cross with inflection. It just crosses. So it's a single 0 there. Good, x plus 1. Now I see a vertical asymptote at x equals -2. So that tells me that in the denominator I have x plus 2. Okay? And I don't see any holes or anything. However, what I do notice is that this function, if we take a look, this function has a horizontal asymptote. It's going to, in the long run, go down to 0. So what does that mean? That means if it's going down to 0 in the long run, it means that if we look at the end behavior, back to the previous 11.4, if we looked at the end behavior, then when I simplify leading term over leading term, I have to end up with an x in the denominator, right? Because it has to go to 0. And so in this case, what I'm going to do is I'm going to, right now, if I simplify x over x, that's going to go down to 1. So that could technically, that could still be a horizontal asymptote, but this graph certainly looks like it's going to 0. And so to do that, I'm going to give myself another factor in the denominator, so that now when I look at the leading term, it's x over x squared, which reduces to 1 over x, which is what this graph kind of looks like in the long run. Okay. Now the next piece of information I have here is the y-intercept of 0.5. And so I don't know what this a value is, but I know that, let's just go over here now. So I know that 0.5 is what I get when I plug 0 in for the x's. And so 0.5 equals a times, that's going to be 1 over 4. Divide both sides by 1/4, and that should be about 2, or exactly 2. And so now we have the rational function is equal to, and here with this a value, you can either leave it out front, or to make it look like a true rational function, put it in the numerator. So 2 times x plus 1 over x plus 2 squared. And that's how we kind of create rational functions based off of the features of the graph. All right. The book from here goes and talks about the holes. So when both numerator and denominator are 0, creates a hole in the function. So that's an undefined value, an undefined place in the function. Got a picture here to show, right? So that's when we use like an open circle to show a hole, if you didn't know what that meant. Yeah, so that's short run behavior. let's go ahead and do an example. Let's do let's try number 8. Number 8 looks pretty good. Okay. So number 8, just so we can have like an example of the type of problems we'll see here. Okay. So we're going to find the x-intercepts, the y-intercepts, horizontal and vertical asymptotes. So our function is h of x equals x squared minus 4 over x cubed plus 4x squared. Okay? What I like to do is I like to write this rational function in factored form because it's going to help us a lot. So let's go ahead and factor this. X squared minus 4 factors into x plus 2 and x minus 2. Divided by, checking here, I can factor an x squared out, leaving me with x plus 4. Okay. So, x-intercepts. How do we find the x-intercepts? Set the numerator equal to 0. So I see x plus 2 and x minus 2. Hopefully we know that that means that we have zeros at x equals negative 2 and x equals positive 2. Okay? Y-intercept. How do we find the y-intercept? We would plug 0 in for all of the x's. So for that, if I plug 0 in, I'm going to have, I'll just show you here, over 0 squared and 0 plus 4, okay? And that's going to reduce to negative 4 over 0. And that's undefined, right? That's undefined. And so the y-intercept, there is none. There is no y-intercept because when you plug 0 in, it's undefined. Interesting. How about the vertical asymptotes? Vertical asymptotes, set the denominators equal to 0. So what are the zeros of the denominator? Well, x squared, that means x equals 0. And so now we just see why there's no y-intercept. It's because there's a vertical asymptote there at x equals 0. And at x equals negative 4. And then the horizontal asymptotes. Are there any horizontal asymptotes? Horizontal asymptotes come from end behavior. So now I'm actually not going to look at the factored form. I'm going to go back to the original. And it's going to be the same. They're going to have the same horizontal asymptotes as x squared over x cubed, right? Leading term over leading term. And that's going to reduce to 1 over x. So it has the same end behavior as 1 over x, which means the limit as x approaches positive and negative infinity is equal to 0, right? That variable is still in the denominator. It's going to go down to 0. So there's an example, number 8, of pretty much some of the problems you'll be doing in this problem set, all right? So that is it for 11.5, and I will see you next time.